circumference. In this module, we discuss random experiment, sample space and events and probability. Random experiment. The base of probability is the reduction of common sense to calculation. The notion of probability originated a few hundred years ago. The theory of probability is arising from the concept of random experiment. A statistical or random experiment is an experiment with more than one possible result, where the experiment can be repeated any number of times under more or less similar conditions, but the result may vary irregularly from one repetition to another. For example, consider the coin tossing experiment. There are two possible results for this experiment. They are head and tail. Even though the tossing is repeated under the same condition, the results are appearing irregularly from one toss to another. That is, for this experiment, there is more than one possible result which is irregularly occurring from repetition to repetition, even though the experiment is repeated under almost same condition. Hence, this is a random experiment. In similar way, the experiment of tossing a dice also can be considered as an example for random experiment with 6 possible results, which are the numbers 1, 2, etc. up to 6 written on the 6 faces of the dice. Sample space. The set of all possible outcomes of a random experiment is called its sample space and is denoted by S. The sample space of the coin tossing experiment is S equal to the set containing H, T, where H denotes the outcome head and T denotes tail. The sample space for the experiment of tossing a single dice with the numbers 1 to 6 written on their 6 faces is the set S containing the points 1, 2, 3, 4, 5, 6. Consider the random experiment of tossing a coin and a dice together. Here, the possible outcome is any of the following 12 possibilities. They are H1, H2, etc. H6, T1, T2, etc. T6. Hence, the sample space of this experiment is the set S of the above 12 elements. The sample space of a random experiment is said to be discrete sample space if it contains a finite or countable infinite number of elements. The above considered sample spaces contains finite number of elements, that is, the first one contains 2 elements H and T, the second one contains 6 elements and the third contains 12 elements. Hence, they are discrete sample spaces. One man is decided to toss a coin until a head appears. Consider the experiment of counting the number of tails occurring prior to the occurrence of a head. The possible results of the experiments are 0, 1, 2, etc. up to infinity. The result may vary from one man to another. Hence, the experiment is a random experiment with sample space S equal to the set containing points 0, 1, 2, etc. up to infinity. Here, the sample space contains infinite number of elements, but we can identify the infinite possible elements as 0 is the first possible element, 1 is the second possible element, 2 is the third, next is 3, etc., etc. Or mathematically, there exists a 1-1 correspondence with the elements of the sample space to the set of natural numbers. Then, the set S is said to be countable. Hence, S is a discrete sample space. The sample space of a random experiment is said to be continuous sample space if it has an uncountable number of elements. Example, consider the experiment of noting the life length of an electric bulb taken randomly from the box of bulbs from a factory. Here, the factory producing all the bulbs under same method, but the life length may vary irregularly from one bulb to another. For a bulb, the life length, let it be in hours, may be any real number in between 0 and infinity. Hence, the sample space of this random experiment is S equal to the set of x where 0 less than x less than infinity. Mathematically, the set S is uncountable. That is, it is not possible to identify which is the first possible life length and which is the second possible life length, etc. Hence, the sample space is said to be continuous sample space. Event. Any subset E of a sample space is called an event. That is, an event is a set which contains some or all the possible outcomes of the random experiment under consideration. If the outcome of the random experiment is an element of E, it says that E has occurred. Example: consider the sample space S containing the points H T of a coin tossing experiment. The events are null set, the set containing the point H, the set containing point the T, and the set containing points H T. These are the possible subsets of S. Mutually exclusive or disjoint events. Any two events of a random experiment having no elements in common are called mutually exclusive or disjoint events. Since disjoint events are having no elements in common, they cannot occur together. Hence, in other words, two events of a random experiment which cannot occur together is called mutually exclusive or disjoint events. The events A and B are mutually exclusive if A intersection B equal to null set. Example: consider the sample space S equal to the set containing points H T. Let the events A1 containing the point H and A2 which is set containing the point T. Here A1 intersection A2 is null set. Hence, A1 and A2 are mutually exclusive or disjoint. A set of events are said to be mutually exclusive if any pair of events of the set is having no common elements. Exhaustive events. If the union of events under consideration is the whole sample space, the events are called exhaustive events. In the above example, A1 and A2 are exhaustive also, because A1 union A2 equal to S. Equally likely events. Out of all the events under consideration, if there is nothing to believe that one event is more probable to occur in a particular trial of the experiment, then the events are said to be equally likely. Or in other words, when all the events under consideration are having equal chance to occur in any repetition of the random experiment, the events are called equally likely. Example: if the coin considered is unbiased, the events A1 which containing the point H and A2 which containing the point T are having same chance to occur. Hence, they are equally likely events. Relations and operations of events. For a random experiment, we have seen that every event is a subset of the sample space. Hence, for the events of a random experiment, the sample space S is the universal set. Equality of events. Two events A and B are equal if every element of A belongs to B and every element of B belong to A. Then it is denoted by A equal to B. Complement of an event. For an event A, complement of A is the event containing the elements of the sample space S which are not belonging to A. Complement of A is usually denoted by A bar, A dash or A complement AC. Sub event or super event. If every element of an event A is an element of the event B, we say A is a sub event of B or B is a super event of A. It is denoted by A subset of B. The null event phi is the subset of any event A and the sample space S is the super event of any event. Union of events. The union of two or more given events is the event whose elements are the elements of at least one of the given events. For two events A and B, their union is denoted by A union B or A plus B. The shaded region in the following Venn diagram represents A union B in each case. Intersection of events. Intersection of two or more events is the event containing the elements which are common to all the events under consideration. For two events A and B, their intersection is denoted by A intersection B or A into B. For three events A, B and C of a sample space S, the following results hold. 1. A union null set is equal to A intersection null set equal to null set, and A union S equal to S, A intersection S equal to A, called identity laws. 2. A union A equal to A, and A intersection A also equal to A, called idempotent laws. 3. A union A complement is equal to S. A intersection A complement is equal to null set. A complement, the whole complement is equal to A, called complement laws. 4. A union B equal to B union A. A intersection B equal to B intersection A, called commutative laws. 5. A union B, the whole complement is equal to A complement intersection B complement. A intersection B, the whole complement is equal to A complement union B complement, called De Morgan's laws. A union B union C equal to A union B union C, that is equal to A union B union C, and A intersection B intersection C equal to A intersection B intersection C, that is equal to A intersection B intersection C, called associative laws. A union B intersection C equal to A union B intersection A union C. A intersection B union C equal to A intersection B union A intersection C, called distributive laws. For the events A, B and C, the sample space S, let us express the following events. 1. All of the 3 events occur. 2. At least one of the 3 events occur. 3. Only one of the 3 events occur. Number 1. All of the 3 events occur means the outcome of the experiment should be an element of A and B and C. The following shaded region contains the elements of A and B and C, which is A intersection B intersection C. Hence, all the 3 events occur is the occurrence of A intersection B intersection C. That is, the event all the 3 events occur is expressed as A intersection B intersection C. 2. At least one of the 3 events occurs happens when the outcome of the experiment is an element of A or B or C. That is, the outcome of the experiment is an element of the following shaded region. The shaded region is A union B union C. Hence, at least one of the 3 events occur is expressed as A union B union C. 3. For the event only one of the 3 events occur, the outcome of the experiment is element of A alone or B alone or C alone. The required event can be shaded as follows. Now, the required event can be expressed as the union of 3 shaded portions 1, 2 and 3. Portion 1 is represented as A intersection B union C the whole complement. 2 is represented as B intersection A union C the whole complement, and 3 is represented as C intersection A union B the whole complement. Hence, the required event is expressed as A intersection B union C the whole complement union, B intersection A union C the whole complement union, C intersection A union B the whole complement. Statistical regularity and probability. Consider a random experiment and let S be its sample space. Let capital A be an event of this random experiment. The experiment is repeated for n times. The event capital A occurred f out of n repetitions of the experiment. Then f is called the frequency of the event A in n repetitions of the experiment, and f divided by n is termed as the relative frequency or frequency ratio of the event A. Consider the sequence of frequency ratios for an event A for various values of n. Then it can observe that as the number of repetitions of the random experiment n increases, the frequency ratio of event A shows regularity and converges to a number, say p. This phenomenon is common to all random experiment and is known as statistical regularity. The converging value p of the frequency ratio of an event of a random experiment is called the probability of the happening of that event. A definition for probability based on the above phenomenon known as von Mises statistical or empirical or frequency definition of probability, which is stated as: if an experiment is performed repeatedly under essentially homogeneous and identical conditions, then the limiting value of the frequency ratio as the number of trials becomes indefinitely large is called the probability of happening of the event, it being assumed that the limit is finite and unique. If capital A is the event, probability of A is denoted by P of A. Based on the frequency definition of probability, the following properties of probability have been proved. Number 1, for any event A, 0 less than or equal to P of A less than or equal to 1. Number 2, for the sample space S, P of S equal to 1. 3, for an event A, P of A equal to 1 minus P of A complement. 4, P of null set is equal to 0, where null set is the null event or impossible event, etc. Another approach to probability is made by famous Russian mathematician N. Kolmogorov. He defined probability as a special type of mathematical function satisfying some conditions or axioms called probability measure. The definition is known as axiomatic definition of probability. Following are some theorems on probability. 1. Addition theorem. Let E and F are any two events, then P of E union F equal to P of E plus P of F minus P of E intersection F. 2. If E and F are mutually exclusive, P of E intersection F equal to P of null set, that is equal to 0. Hence, P of E union F equal to P of E plus P of F. 3. Addition theorem for three events E, F and G. P of E union F union G equal to P of E plus P of F plus P of G minus P of E intersection F minus P of E intersection G minus P of F intersection G plus P of E intersection F intersection G. 4. If B subset of A, then number 1, P of A intersection B complement equal to P of A minus P of B. 2. P of B less than or equal to P of A. 5. For any two events E and F, P of E intersection F complement union E complement intersection F equal to P of E plus P of F minus 2 times P of E intersection F. Probability classical approach. The classical approach to probability is based on a random experiment with the sample space containing finite number of elements with the probability of occurrence of all the elements are same, that is equally likely. Historically, the classical definition is the one of the oldest definition of probability. The definition is as follows: if a random experiment or trial results in n exhaustive, mutually exclusive and equally likely outcomes, out of which m are favorable to the occurrence of an event E, then the probability of occurrence of E is given by P of E equal to number of favorable cases to E divided by total number of cases, that is equal to m divided by n. Illustration: consider the random experiment of tossing of a die with numbers 1 to 6 written on its 6 faces. The sample space S equal to the set containing points 1, 2, 3, 4, 5, 6. Assume the occurrence of all the 6 faces are equally likely. Consider the event A equal to the set containing points 2, 3, 5. Here, out of the 6 possible mutually exclusive, exhaustive and equally likely outcomes of the experiment, 3 are, that is 2, 3 and 5 favorable to the event A. Hence, by the definition, P of A equal to 3 divided by 6, that is equal to 1 divided by 2. Consider the random experiment of picking a card from a well shuffled pack of 52 playing cards. Consider the event of getting an ace. There is nothing wrong to assume that all the 52 cards having the same chance to be picked out in a trial. Out of these 52 cards, 4 are ace cards. That is, out of the 52 equally likely, mutually exclusive and exhaustive possibilities of the experiment, 4 are favorable to the event under consideration. Hence, the probability of the event of getting an ace is 4 divided by 52. Classical definition makes the probability calculation of various events when the sample space under consideration is finite with equally likely possible elements. Probability calculation illustrations. Problem: a card is chosen at random from a well shuffled pack of 52 cards. Find the probabilities of getting a card of number 1 a king, number 2 a red queen, number 3 a black card or a queen. Solution: let capital A be the event of getting a king card, capital B be the event of getting a red queen, and capital C be the event of getting a black card, and capital D be the event of getting a queen card. The content of the pack of 52 cards is 4 sets of 13 cards each named as heart, diamond, spade and club. Among these, spade and club cards are black in color and heart and diamond cards are red. Each set of 13 cards consists of a king, a queen, an ace card and cards with numbers 2, 3, 4 etc. up to 10 written on them. Hence, in a pack of cards, there are 26 black cards, 26 red cards, 2 black kings, 2 red kings, 2 black queens, 2 red queens, 4 ace cards etc. The problem are solving under the assumption that all possible outcomes are equally likely. The random experiment under consideration is having 52 equally likely possible outcomes. Number 1, the pack contains 4 kings, that is 4 out of 52 cards are favorable to the event capital A. Hence, P of capital A equal to 4 divided by 52. 2. The pack contains 2 red queens, that is 2 points are favorable to B. Hence, P of B equal to 2 divided by 52. 3. The event of black card or a queen is represented as C union D. By addition theorem, P of C union D equal to P of C plus P of D minus P of C intersection D. Pack of card contains 26 black cards. Hence, P of C equal to 26 divided by 52. Pack of card contains 4 queens. Hence, P of D equal to 4 divided by 52. Out of 52 cards, 2 cards are black queen cards. Hence, P of C intersection D equal to 2 divided by 52. Now, P of C union D equal to 26 divided by 52 plus 4 divided by 52 minus 2 divided by 52, that is equal to 28 divided by 52. Problem: 2 unbiased dice are thrown. What is the probability of getting sum of the numbers shown is less than 5? Solution: when 2 unbiased dice are thrown, we can expect any of 36 equally likely possible outcomes. The sample space is the set S contains the ordered pairs 1 1, 1 2, 1 3 etc. 4 5 etc. 6 6. Let capital A be the event of the sum of the numbers shown is less than 5. Out of the 36 outcomes, the following 6 outcomes are favorable to the event capital A. The ordered pairs 1 1, 1 2, 1 3, 2 1, 2 2 and 3 1. Hence, P of A equal to 6 divided by 36, that is equal to 1 by 6. Now, let us summarize the session. A foundation of probability is laid in this module. The concept of random experiment, sample space, event are discussed in detail. Various types of sample spaces and events are considered. Frequency definition, axiomatic definition and classical definition of probability are explained. Many properties of probability are pointed. Some numerical problems on probability are also solved. Before we attend the next unit, please try to answer the following questions. 1. For the events A, B and C, write down the expression for 1. At least one of A, B and C. 2. Exactly 2 of A, B and C. Question 2. Write down the sample space of a random experiment of simultaneous tossing of 3 coins. Question 3. 2 fair dice with the numbers 1 to 6 on their 6 faces are tossed. Find the probability of the event of getting sum of the numbers shown is between 6 and 10. Next, in a particular community, Let capital A denote the event of smokers and capital B denote the event of chest patients. P of A equal to 0.8, P of B equal to 0.2 and P of A union B equal to 0.7. Find the probability of the event of both smokers and chest patients. Books for your reference are 1. Marcelo Pagano and Kimberly Guerrio, Principles of Biostatistics, Signage Learning. 2. Mehdi J. Statistical Methods and Introductory Text, New Age International Private Limited. 3. Bud B.R., Sri Venkatramana T. and Madhav Rao K.S. Statistics, a Beginner's Test, New Age International Private Limited. 4. Gupta S.C. and V.K. Kapoor, Fundamentals of Mathematical Statistics, Sultan Chand and Sons. 5. Daniel W. Biostatistics, John Wiley Sons. Hope you enjoyed this session. See you next time. Until then, goodbye.